Hello everyone, my name is Qian Ding. I'm a PhD student at ETH Zurich. So in this presentation, I want to talk about our study of the scaling effects on the plasmonic enhancement of the butt-coupled waveguide photodetectors. Now, in the following of this talk, I will first give you a brief motivation of why we are interested in the plasmonic waveguide photodetectors. Then I will present to you the performance analysis for the non-plasmonic device. After that, I will discuss the optical and electrostatic impacts of a plasmonic structure with a given size, and moreover, how these impacts affect the performance. And at the end, we will see how the plasmonic influence on the device performance depends on the size of the plasmonic structure. As you may know, one of the main technical challenges to achieve the chip-level optical interconnects is the fabrication of CMOS-compatible nanoscale photonic devices, which requires a high-quality monolithic integration of 3-5 materials with silicon. Fortunately, this problem can be potentially solved using the so-called TAZE technology invented by IBM Zurich in 2005. And the figure on the bottom left demonstrates our big vision of the on-chip optical communication system that can be fabricated using this method. Now, as you can see, at the receiver end, the design of highly integrated waveguide coupled photodetectors with high speed and high responsivity are required. Now, we have designed 3 different devices to achieve such a lateral coupling between the silicon waveguide and 3-5 photodetector in our work last year, namely the butt-coupled device without and with N offshoots, as shown in the left blue and middle green box plot on the top, and the side-coupled device shown in the right red box. Their corresponding optimized performance can be extracted from the frequency response curves shown in the bottom right figure, although the side-coupled device turned out to be the best one, as indicated by the red curve. It seems that there is still some space to improve the performance of the butt-coupled device with N offshoots, which is represented by the green curve. And adding a plasmonic structure should be a very promising option. This is because so far several studies have demonstrated that plasmonics can indeed improve the performance of photodetectors. As you see from the few examples listed on the left, it can improve the bandwidth of Schottky type photodetectors up to the sub-gigahertz range, and also it can boost the internal quantum efficiency by almost a factor of 2 in the conventional vertically stacked PIN photodetectors. Now, given these reported positive impacts, it would be very interesting to see if the presence of a plasmonic structure could also help improve the performance of our lateral butt-coupled waveguide photodetectors, and how this impacts depends on its size. To find answers to these questions, we need to first understand the physical mechanisms that limit the performance of the corresponding non-plasmonic device. As we see from the left figure, its frequency response curve shows an unusual triple cutoff feature, with the lowest cutoff frequency in tens of megahertz range, the middle one in tens of gigahertz range, and the highest one around 1 gigahertz. Now, this indicates that the device speed is limited by 3 transport mechanisms that are present in the device, and we want to figure them out, especially the lowest one, because it eventually limits 3 dB bandwidth. The commonly used method to find these origins in textbooks often relies on the analytical strategy, with the assumption that a uniform distribution of optical generation and the electrical field in the eye region exists. However, due to the complex structure of the targeted device, both of them actually follows a highly inhomogeneous distribution pattern, as you see from the color map plot on the right. So the analytical analysis is hardly feasible in our case. Now here we introduce a simple reference method to sort out the different limiting mechanisms. This is done by simulating the frequency response curve of the same device, but with artificially scaled mobility of different carriers in different regions and then compare them with the original one. This method could work because the bandwidth limiting mechanisms in the PIN photodetectors originate from either the carrier drift or the carrier diffusion process, and both of them have a dependency on the carrier mobility. For example, for a type of carrier in the low field region, when we strongly downscale its mobility, say by a factor of 100 or so, one of the cutoff frequencies vanishes, and then it should relate to the diffusion of the corresponding carrier in that region, because if it's only limited by the drift process, the cutoff should simply decreases rather than disappears. Similarly, in the high field region, if a cutoff scales up with roughly the same factor as we increase the mobility of one type of carrier, then it's limited by the drift process of that carrier. After considering all possible combinations of the carrier types and device regions, the speed limiting processes in the non-plasmonic device can be easily figured out. As we see from the left figure, the middle and highest cutoff frequencies are limited by the drift of holes and electrons in the high field intrinsic region, while the lowest cutoff frequency is found limited by both the hole diffusion from silicon waveguide and its drift in the low field intrinsic region. Now, the limitations from the drift processes are already well understood in the PIN photodetectors, but the physics related to the hole diffusion from silicon waveguide seems a bit abnormal here. So this diffusion process exists actually due to the presence of a hole gradient density near the intrinsic region and silicon waveguide interface, as you see in the right middle color map plot. And the formation of such a gradient is understood as follows. On the one hand, the valence band bends upwards in the silicon, and a small hole potential wheel forms near the intrinsic region and silicon waveguide interface, which leads to a higher hole concentration there, as shown in the right bottom band diagram. On the other hand, the electric field in the silicon is too low to collect these holes by fast drift process, as shown in the right upper plot, and the holes there have to first diffuse into the intrinsic region and then get drifted to the P contact. Now, this idea can be further proved by simulating a slightly undoped silicon waveguide with the same concentration as in the intrinsic region, where this hole gradient doesn't exist at the beginning. And indeed, the lowest cutoff frequency vanishes in this case, as shown by the magenta dashed curve in the left figure. Now, knowing the origins of each cutoff in the non-plasmonic device, the plasmonic impact on the device performance can then be easily detected by comparing the frequency response curves of both devices. But before that, we need to think about how the optical generation and the electric field are changed when a metal strip is placed on top of the intrinsic region to form the plasmonic device, because their distribution ultimately determines the device performance. Now, from the optical point of view, the original dielectric mode in the intrinsic region now is hybridized with the SPP mode formed at metal and intrinsic region interface, as you see in the left upper figure, and as a consequence, the optical generation is shifted closer to the metal interface and gets enhanced there. But when we consider its integral over the entire device region, in other words, the total amount of optically generated carriers per second, the plasmonic improvement is negligible, as you see the numbers listed on the slides. On the other side, once the metal strip is placed on the intrinsic region, a Schottky interface is formed, and in this work, we assume a barrier height of 0.6 electron volt. This will significantly change the electrostatics, as you see from the comparison of electric field in the left bottom figures. The field is strongly enhanced near the intrinsic region and silicon waveguide interface. It becomes weaker as getting closer to the PI junction. Such a position-dependent impact comes from the fact that the Fermi level in the intrinsic region gets energetically closer to the valence band edge as we go towards the p side due to the formation of the pi junction, as we say from the right bottom band diagram plotted along the pi silicon direction. This Fermi level change with respect to the band edge further changes the band alignment in the formation of the Schottky barrier and leading to a position-dependent band bending in the intrinsic region close to the metal interface. For example, when it's far from the p side, as shown by the position labeled by the blue dashed line, the Fermi level is close to the conduction band edge, and the Schottky barrier induced band bending is strong as expected, but at a position that is very close to the p side, as indicated by the orange dashed curve, the Fermi level locates far below the conduction band edge, and consequently, the band bends only slightly there, which explains the weak field. After understanding the optical and electrostatic impacts induced by the metal strip, we could now have a look at how it changes the frequency response of the device. Here we assume a 500 nanometer long, 140 nanometer wide, and 60 nanometer thick metal strip placed symmetrically on top of the intrinsic region, where the intrinsic region has the same length as the metal strip, but it is 60 nanometer wider. As we see from the left figure, all three cutoff frequencies are improved in the plasmonic device, especially the lowest one that is limited by the hole diffusion from silicon actually vanishes. So this indicates that the former present hole density gradient in the non-plasmonic device disappears after the placement of the metal strip, as we see from the comparison in the right color map plots. Now this elimination of such a hole density gradient actually originates from the enhanced electric field near the intrinsic region and silicon waveguide interface due to the formation of Schottky barrier in the plasmonic device, as we discussed in the last slide. Now let's see how these impacts change when we scale the size of the plasmonic structure, namely the length, width, and thickness of the metal strip. First, we vary the strip length from 500 nanometer to 300 nanometer with a step of 100 nanometer, while keep the width and thickness fixed as 140 nanometer and 60 nanometer. The length here is measured starting from the pi junction. As shown in the left figure, the strip length mainly influences the original lowest cutoff frequency. So when the strip becomes shorter than 400 nanometer, it starts to reappear again in the plasmonic device, as indicated by the black dashed response curve. And this is because with a shorter metal strip, the field enhancement in the intrinsic region is shifted away from the intrinsic region and silicon waveguide interface, and as a result, the hole density gradient shows up again due to the absence of the field there, as we see from the color map plots on the right. Next, we scale the strip width from 180 nanometer to 60 nanometer with a step of 40 nanometer and keep the strip length and thickness unchanged as 500 nanometer and 60 nanometer. From the response curves shown in the left figure, we see that the strip width mainly affects the highest cutoff frequency that is related to the electron drift in the intrinsic region, where it drops with a narrower strip. And when the metal strip is narrowed down to 60 nanometer, the improved middle cutoff frequency that is limited by the hole drift also drops back as in the non-plasmonic device. This dependency comes from the fact that as the metal strip becomes narrower, the enhancement of the electric field near the Ni junction gets weaker, as shown in the right color map plots, which causes a smaller drift velocity of the carriers and consequently a lower cutoff frequency. As the last step, we vary the strip thickness from 20 nanometer to 100 nanometer with a step of 40 nanometer. And from the response curves shown in the left figure, we can see that the metal strip thickness has little impact on the device performance, which can be explained as follows. First, changing the strip thickness doesn't influence the electric field distribution, as you see from the right upper color map plot. This is simply due to the fact that the electrostatic impact of the plasmonic structure is ultimately determined by the Schottky barrier height. On the other side, a thicker metal strip could slightly improve the optical generation, as shown in the bottom right plot, which indeed gives a little bit higher quantum efficiency when we compare the green and black dashed curves in the left figure. But the overall improvement is too small to give any practical useful result. Now it's time to summarize this talk. We first introduced a simple reference study method by scaling the carrier mobilities to figure out the speed limiting mechanisms in the non-plasmonic device. And we found that it is actually limited by the lowest cutoff frequency that is caused by the hole diffusion from the silicon waveguide. And this could be a potential problem for the waveguide coupled photodetectors. And then we showed that the presence of a metal strip on top of the intrinsic region has a larger impact on the electrostatics than on the optics, and the lowest cutoff frequency can actually be eliminated in the plasmonic device with assumed 0.6 electron volt Schottky barrier height. Furthermore, we found that the metal strip largely influences the lowest cutoff frequency, while the width of the metal slightly affects the two higher cutoff frequencies, and the metal thickness is barely relevant for its performance. And that's all. Thanks for your attention.